The topic of my presentation is methods and models of dynamic wireless energy transfer based on hybrid coupling. So I am PhD in technical sciences, lecturer in Chernihiv National University of Technology. I have more than 10 journal papers, more than 20 conference papers, patent applications, books, and more than 10 years of experience in research, embedded systems, and power engineering in different countries. So the project is related to the area of energy and energy efficiency. The field is electrical power engineering, electrical engineering, and electromechanics. The duration is 3 years, and the estimated budget is 4.5 million. The host institution is Chernihiv Polytechnic National University. So the project motivation and problem statement. At this moment, mainly the existing wireless power transfer systems are static. So in the research about the dynamic charging remains inefficient and complex. Inductive-only systems suffer from such a list of problems like efficiency drop for different misalignment, high-frequency losses, large magnetic components, and positioning sensitivity. So we need to find some solution which will be stable, scalable, and efficient to be able to be used in dynamic wireless power transfer. The main aim is to develop such methods, models, and experimental prototypes of hybrid inductive capacitive dynamic wireless power transfer system. So key objectives is to develop improved model, design special sensorless activation methods, create models, and to represent and to publish all these models as well as results accordingly to the open science principles. We will be using different tools for analytical modeling, for FEM simulation, for circuit simulation, and of course we will perform experimental validation. We expect to get efficiency up to 90%. In dynamic case, 10-20 reduction in size and weight of the system, stable output power under dynamic movement, and reduce idle losses. The project leader is Bogdan Pakhalyuk. Responsible executor is Viktor Shevchenko. Our team consists of 8 people, 2 PhD, 4 PhD students, and 2 students. So this is our team. And the impact and exploitation of our research. The research will give a new hybrid modeling framework. We will develop a special software which will be used to develop new ideas and to verify these ideas for the case of hybrid coupling. We will publish open data sets, and we have already published some of them. We plan to publish more than 3 Scopus publications, and it will be good for the economics because it will give a new step in terms of development of electric vehicle, in terms of logistics, and reduced charging infrastructure costs. So the project plan looks like this. The plan is divided into 3 years and into 8 working packages. You can see we have a plan for the publications, for the conference papers, for the data sets, open source, and for patent application. Also, we plan to develop a startup team and to find some investors or which will be interested in our technology. So now let's dive into wireless power charging technology directly. So this technology gained high interest in last years because of its reliability and maintain costs. And now this solution can be used to perform charging from hundreds of watts up to even megawatts in some cases. So it can be used in car charging, in light vehicle charging like bikes, for example, in different low power charging, for example, for the phone charging, toothbrushes, or for example, even for the pacemaker charging, which will be a breakthrough technology because there is no need to make innovation in order to charge the special battery or the pacemaker. From the physical structure, we can say that wireless power transfer the energy can be transmitted by the light, acoustic, by the inductive power transfer, magnetic resonance, and capacitive power transfer. So the interesting elements for us is inductive power transfer and capacitive power transfer. Why? Because these technologies give possibility to transmit more energy and more safely. So the dynamic wireless technology is one of the main field of research in wireless charging, and you can see some prototypes of 20 kilowatts. So this technology will give possibility to charge during movement, decrease size of the battery, decrease the necessity in deep discharge during walk of the car, decrease pollution. Transfer facilities are underground, so it will be good for example, different recreation areas, for historical places. There is no necessity to add different wires, like in case of the trolley buses and so on. We will not spoil the look of the historical places. And we can transmit comparably high power. But we have low efficiency and we have safety questions. Let's see a bit of the history. We can divide the history into three periods. First period is devoted to the first interest in technology, but we were not ready to develop any feasible solution. The second period is first attempt to make some solutions, not efficient, but still they were operable. And now this is the solutions which can be used in our everyday life. So first period, as you can see, some of the ideas, patents were made even in 19th century, and they had the idea of special metal core, which was moving inside the coil, and by this moving metal core, we were able to activate particular transmitter coil. So we can say that this was something like a special switch, which was activated only when the receiver, in our case some car or bus, was approaching to this coil. Another idea also was proposed in that year, and in this case they were using a special array of capacitors. This significant step was made by even Ukrainian researchers in 40s, but as you can see, in such a developed system, they were able to transmit 2 kilowatts of energy, but the efficiency was only 4%. You can imagine how much losses they were getting. First prototypes, which were more or less feasible, were made in 70s in Berkeley lab. As you can see, they gained efficiency up to 72%. Oh, sorry. Okay. So, and now different researchers were made in, for example, Oak Ridge National Laboratory. They improved the battery size, energy transfer, but you can see that they are using special sensors to activate a particular part of their road or our track. And fast in charge projects also they have special switches to activate a particular coil, and they have special magnetic sensors to know where the car is situated. So let's dive to the basic idea of inductive power transfer. As you can see, we can say that our energy transmission is something like a transformer with a gap. So if we will split transformer, we will have this gap. So we can say that one part will be related to the transmitter, second part will be related to the receiver. In order to perform energy transmission, we have special switching elements to get high frequency oscillations, and we have rectifier to get the DC voltage on the output. As you can see, we have special capacitors which are connected in this case in series with the coils. So why these capacitors are used? These capacitors are used to compensate the reactance of our coils and to be able to transmit more energy without necessity to drastically increase the input voltage and other elements. There will be no necessity, for example, to increase the operating voltage of the transistors, diodes, and so on and so on. So we can see three models. First model without any compensation, second with compensation on the secondary side, and with compensation on both sides. If we will try to measure the resistance on these input terminals, in first case we will see that the equation will look quite big, and as you can see, we have the resistances of our coils, the resistance of our load, and all these resistances will limit the power transfer capabilities of our system. In case if we will add this compensation capacitor, as you can see, the equation is becomes more simple, but still we have influence of this primary side coil. If we will put two compensation capacitors, as you can see, we have quite simple equation, and which is interesting in this equation, as you can see, this is fully resistive load, so there is no reactive there is no reactance in our impedance. And if we will compare all these three solutions, we will see, for example, that in terms of efficiency, you can see that first solution give a very low efficiency. And if we will compare and see the output power, we can see that third solution is able to transmit a drastical amount of power with the same input parameters and same load. And the same situation can be seen, for example, on the primary side current, and also we can see the phase of the primary side current. And as you can see, in third case, the phase is 0, which means that even for different loads, we are still operating in the resonance. This is plots for different output load, And if we will change the coupling coefficient, this is like the distance between transmitter and receiver, we will also see that in a third case, we are able to transmit drastical amount of energy with high efficiency, and we will be operating in resonance, while in other cases, we will not have the possibility to fully use all elements of our system, or there will be necessity to drastically increase the input voltage in order to get the same output power. There are other types of compensation. As you can see, we can connect our capacitors not only in series, we can connect them in parallel, like from the primary side, and we can make same for the secondary side. As you can see, or we can even make some more complex combinations to get some additional advantages in this case. So also the resonance will give us a possibility to simplify the analysis of our model. On this plot, you can see that if we will analyze the impedance of our system, and if we will try to pass all the harmonics of the input signal, we will see that the drastical amount and the main energy will be transferred only on first harmonic. So only on the switching frequency, we will transfer more than 97% of the energy. So in this case, we can replace complex system of switching elements just by source of sinusoidal input voltage. The same can be applied to the output. Instead of this complex rectifier, capacitor, and output load, we can use a resistor which will consume the same energy as in AC mode, which will be consumed by the another load, another resistor, let's say, in the DC mode. Also, in some cases, for example, for the small output load, I mean, small value of the resistance or high coupling coefficient, we can get the pole splitting or bifurcation phenomenon. And this phenomena should be taken into account, and we will see this phenomena in slides, in the simulation slides. Also, we need to take into account special standards which limit the operating frequency and output power. As you can see, for example, in some cases, in some standards, we can transfer a drastic amount of energy like kilowatts, but we are limited to comparably small operating frequency. If we will go to high frequency, we will have limitation to transfer something like 500 of watts. There is no possibility to transfer kilowatts without violating their standards and without making this system unsafe. The main part is a coupled coil, and the design of these coupled coils play a crucial role in our research. And if we will analyze different designs, we will see that these designs have many limitations, and we need to find some kind of trade-off between all these parameters. And for example, on this plot, you will see that different solutions will have advantage in terms of efficiency or in terms of power density, and there will be no, let's say, a good or optimal solution in terms of all parameters. All in all, this will be some kind of trade-off between different parameters we are interested in. And if we will see the the topologies for multiple transmitters, we will see that these topologies use quite huge amount of switching elements in order to perform energy transmission in dynamic. So in this case, as you can see, for two transmitters, we have 8 transistors, or we have 8 transistors for 3 receivers, and the same 3 receivers and 6 transistors. So there is necessity to find some kind of low redundancy solution, which will be quite simple to be able to be implemented in real life, to be feasible in terms of economical or aspects also. So, and our idea is to use hybrid inductive and capacitive coupling. So we will use not only inductive power transfer, but also capacitive power transfer. In this case, additionally to resonance operation, our capacitor will be acting also like a special switch, will be create a current flow path. By adding this element, we will perform activation without any position sensors. And also, this approach will give possibility not to utilize coils which are not coupled to our receiver. So we will not send any energy if no one will get this energy. So we will not make non-coupled coils, something like antenna, which will be sending energy without any receiver. The idea is shown here. For example, as you can see, this is a design. We have special capacitors on the receiver side and capacitors from the transmitter side. This is a receiver coil and 3 transmitter coils. And as you can see, as soon as we will move our receiver under the transmitter, let's perform this. As you can see, we are approaching, and at some moment we have overlapping of our capacitor plates, and this will give the path for current to pass our transmitter circuit. And in this case, we will transmit the energy. As you can see, for example, in this case, without overlapping, there is no path for the current to go through our circuit, so we will not send any energy. And this system will give such advantages. We will operate in sensorless operation, as I said, low EMF emissions. Also, our capacitor will be working something like a shield, and it will be shielding the energy which is transmitted between the coils. We will have low copper usage if we will operate at high frequency. We can scale it to multi-phase track. As you can see, we can use regular conventional inverter, and we can connect it to multiple transmitters. So there is no necessity to make inverter for each transmitter coil, and only the coupled case, in the coupled case, we will send the energy. And also, as far as this system becomes quite simple from terms of circuit structure, not of course from the physical structure, but from the terms of topology, it will be more simple. So we will be able to simplify the control. We will be able to perform zero voltage and zero current crossing operation. This system can be implemented, for example, in overhead cranes like this. As you can see at this moment, we are using special wires which supply this like moving platform or moving element. It can be used in factory automation, in different linear motors, for example, like this, or we can use it in electric public transport or smart logistic, for example, in monorail trains. This topology can be updated to different interesting structures, which are shown here. For example, we have single coupling solution. We have the same solution, but with special additional coil, as you can see, L3. We can make solutions with double coupling. And as you can see, in this case, these three solutions are double loop. As you can see, we have two loops. And in this case, we are operating in a single loop case. So these models were already tested. We have developed a special environment in Python, which is using SymPy and NumPy libraries to perform symbolical and numerical operations. And as you can see, as far as we are using this first harmonic approximation, we are able to use a quite simple model to perform analysis. To the moment, we are operating in the resonance. And on these plots, we can see different simulation results for all six topologies. And for example, let's see this case. We see that we have these two peaks. This red, this is a resonance frequency, and as you can see, we are getting this frequency splitting phenomena, which I was saying earlier, and we have like two resonance. What we should take into account in this case? In this case, we can see, if we will see the input impedance, we will see that and if we will see the phase of our primary side current, we will see that we have three resonances, this one, this, and this, three resonances. But the resonance at our switching frequency, at our tuned frequency, is not able to transmit a drastical amount of energy. Why? Because in this case, the input impedance is drastically high. So even if we will be operating in the resonance, but if we will have this frequency splitting phenomena, we should take this into account and operate on one of these peaks and not on the switching frequency. So if we will compare all these topologies, we will see that some of the topologies give advantage in terms of power transfer capability, and other topologies give advantage in terms of drastically decreasing their air capacitor size, because as you can see, this air capacitor is one of the elements which should be well optimized, because the size of this capacitor can be quite big if we need to get quite valuable value of the capacitance. So there is necessity to find some kind of solutions which will be a trade-off between power transfer capabilities as well as size of this capacitor. And let's see also some results preliminary. We have already developed a low power experimental set, as maybe I can zoom it a little bit. We can see that we have three transmitter coils. We were testing these air capacitors. This is our couple coil, inverter, and this is a moving platform. Also, the basic idea was shown on wireless power transfer conference, in 2022 in France. And also we got patent in Latvia for this idea. Now we are working with the design of the air capacitors. In this moment, we are making research of different designs, and we are making experimental prototypes of different designs. For example, you can see the flat plate design, the design with something like vertical plates and with the triangular plates. And these plates are covered with copper by the electroplating technology. As you can see, a special plate with the copper is given the copper, and our model is being covered by the conductive material. So this is the end of my presentation.